Okay, I'd like to welcome everybody to the fifth series of EFCE Spotlight Talks. So the topic today is innovative characterization techniques for particulate and crystallization processes. This is going to be chaired by Martin Morgeneyer. He's the chair of the Working Party on Characterization of Particulate Systems, and Daniele Marchisio. He's the chair of the Working Party on Crystallizations. So firstly, who am I? So I'm the current scientific vice president of EFCE. So effectively, I'm the focal point of all activity, all scientific activities carried out by the Federation. So my background is in process safety. I've had experience of that more than 30 years within industry and 5 years within academia. So I've been involved with EFCE for more than 20 years, and I've been a member of the executive board for the last 10 years. So just going to give you some background to the Spotlight series. So some of you may not be familiar with them and may not have been involved with them before. So firstly, say, what is EFCE? So EFCE is the European Federation of Chemical Engineers. Its membership consists of all the national associations representing the chemical engineering profession across Europe. So it doesn't have individual members, it's actually national associations. So for example, IChemE would represent the UK, DECME would represent Germany, SFGPE represent France, and so on. So EFCE covers more than 30 countries, and we represent more than 100,000 chemical engineers. Most of the activities of EFCE are carried out through working parties and sections. So working parties focus on specific topics within chemical engineering. So examples, thermodynamic and transport properties, loss prevention, and clearly the two working parties are represented within this spotlight talk. Their activities are to share and promote knowledge, expertise, and best practice within their particular topic area. Sections address much wider issues, really where they involve a multidisciplinary approach to the particular topic. So examples of sections are, there's a section on energy, section on food, and so on. Altogether, there are 20 working parties across EFCE and 7 sections. And within those working parties and sections, there are around 1,000 volunteers, and the volunteers are experts within their own fields, drawn from both industry and academia. In terms of the activities of EFCE in conferences, seminars, and workshops, so we run a series of European Congress. Firstly, the major activity is the European Congress on Chemical Engineering. So this is something that is a major conference covering all aspects of chemical engineering, and this happens every 2 years. We run this conference jointly with the European Congress on Applied Biotechnology, ECAB. So the next conference is going to be this year in Berlin, and it's running between 17th and 21st of September. It's going to have 9 topic areas, and there will be 15 parallel sections on the conference. So that's our major conference that we operate. We also operate some one-day seminars on new technologies. So they're called the European Forum on New Technologies. These are actually in-person events, not webinars. Typically a one-day event, and the next event is the 6th in the series, and it's to be held in Palermo in October. And that's going to be energy, environment, and digital transformation. And finally, what we're on now is the series of Spotlight Talks. So the Spotlight Talks were devised and overseen by Martin Poo, who's running this particular session today in terms of operating the webinar. So these were initially established to maintain communication during COVID. and they were so successful that we decided we want to continue to operate them post-COVID. And to date, this is the 5th in the series, but up to at the end of the 4th, we had more than 600 attendees on the webinars. The webinars are recorded, and if you want to go and have a look at past webinars or look at this again on the future, you can find it on the EFCE YouTube channel. That's all I want to say, and I'd like to hand you over to the I think Martin is the first to take over. To the floor is yours. Thank you.
Yeah, hello everybody. This is Martin Morgeneyer. I hope you do hear me perfectly well. I'm from Compiègne University of Technology and from SFGP, such as Martin Poux. We are very happy to host this meeting today, and I'm looking on the screen. I see that there are some 40 participants interested in particles, characterization, and so on. And this at 9 o'clock in the morning. So I feel a bit less like being alone in my discipline. And I'm very happy that we made it and we gathered these 40 people. There are many things to say, but also very few things about our working party. So I'm working for the working party characterization of particulate solids, CHOPS. You can easily find the CHOPS working party on the EFCE website. And there are plenty of things to say, but I want to summarize this in a single sentence. Just join, just make your way to our working party, just contact us, send me an email. We are happy to invite you to one of our online sessions also, where we are discussing particle characterization related topics, so scientific topics amongst people from universities such as me, but also amongst many, many people working in industry and working, for example, for the particle analysis equipment manufacturers. So you have the state of the art in terms of particle systems characterization in our working party. So please feel free to join our working party. So if you see contributions today, or which you enjoy, or you enjoy the networking today, just contact our working parties. We are always happy to add you to our meetings. I think Daniele wanted to say some words.
Yes, I'll be very quick. So my name is Daniele Marchisio. I'm chairing the working party on industrial crystallization. In our working party, we are mainly interested in fundamentals of crystallization, investigating nucleation, growth, aggregation, and breakage, but also industrial applications of crystallization, how to run a crystallizer, how to control a crystallizer, how to control the particles and the crystals that you produce in a crystallization process. And of course, it was sort of natural for us to plan this spotlight talk as a joint event between these two working parties, because we do a lot of work in precipitating and crystallizing particles. And in the other working party, there is a lot of focus on characterizing these particles and these crystals. I just want to mention before handing it over to the first speaker that in the summer, we have two important events planned. Maybe some of you are already registered, but if not, mark it down. There is the B-Week meeting, which is the industrial workshop on the International Workshop on Industrial Crystallization, to be held in August, at the end of August in Stockholm, and then the ISIC, the International Symposium on Industrial Crystallization, to be held in Glasgow in the first week of September. So hopefully I'll meet in person some of you there. So I think we can go ahead and introduce the first speaker. So Martin, you're gonna do this, right?
I'm happy to find back my camera. Yeah, maybe the first speaker will be Simon. Simon, could you just begin sharing your screen? Which is the crucial moment we learned preparing this.
Maybe while Simone is sharing the screen, I just want to remind all the attendees that if they have questions, they can ask them through the question and answer box that they see at the bottom of the screen, and all the questions will be answered at the end.
Yeah, very good. So our first speaker will come from Munich today, Simone Schiele from the Technical University of Munich. And he will introduce his work on microcomputer tomography for 3D particle characterization. And I think this first topic very well illustrates the multifold possibilities of characterization methods for particulate systems. So Simon, the floor is yours.
Yeah, thank you very much. I will start with the, I will not start, wait a second. Now I will start with the question, why do we actually need 3 dimensions? And we all know, I guess, that the state of the art is 2-dimensional imaging. And it's great because it has online capabilities, so we can look inside processes while they are running, and even might be able to use that for control of shape and size of particles. And we are also talking about crystals here, and basically in any crystallization paper, you will probably find an image of some sort of the crystals. And I just took 3 random pictures of 3 publications that I found. And in the first one here, for example, you can see a picture that is probably an inline image of something that you might guess is probably needle shaped, but it's like really hard to judge the size and the shape of these particles here. And then there are like other pictures, 2-dimensional images, probably taken by a microscope here, where you see lots of crystals that are nicely faceted, but it's really hard to tell whether they are agglomerated, for example. And there are concavities of these crystals. So if you're interested in that, these 2-dimensional images will also limit the information you have. And then there's also very accurate electron scanning microscopy, where you can look at the surface very accurately, but then again, we don't know whether these are platelets, whether these are cuboids. So as a more general example, I can show you this projection and ask you, how does that particle look like? And one would probably guess it's something that is kind of spherical, maybe cuboid, but you wouldn't have guessed that it's that particle here. So this is what motivates 3-dimensional imaging, which I will be talking today. So it's a very powerful tool if we have very complex shapes that might be concave particles like agglomerates, or if we have asymmetrical particles. And another great feature is that we can also look inside of the particles. So if we have porous particles, it might be also very interesting to look inside of them. The state-of-the-art technology to generate 3-dimensional images is microcomputer tomography, which is basically a CT, like as we know it from the hospital. We have an X-ray source that is transmitted through an X-ray source that's transmitted through a sample and is then detected by a detector, and then we get an X-ray image. And the key about tomography is now that we can rotate the sample, get many different tomographies, many different X-ray images, and then use these images to generate a 3-dimensional image. And this is great to get very accurate images, but also takes quite some time. So one of these measurements takes roughly 1 hour. Like there's some that take 3 hours, some might only take half an hour, but that's kind of the ballpark here. All right, and then in this image here that I took from a paper from my colleague Tiana, we have a bulk of crystals, and then we can take out single crystals and look at them very accurately. And yeah, and then we can, what she did in her PhD was to detect faces of these crystals here and describe them. This is done during 3-dimensional Huff transform, and then we can describe these faces using planes. And then we have a mathematical concept that describes the crystals, and then we can do very accurate analysis and also do modeling and simulations. We also have other applications than crystallization. For example, some colleagues of mine are looking at filamentous fungi, which they also take samples, or they take samples from a bioreactor and then look at these fungi here. And the first obvious thing that we can see is they become larger over time, which is kind of what's also interesting, but kind of boring. And we can have very powerful tools based on three-dimensional images that we can detect the center of these and detect where the spores agglomerated and basically how those particles are generated and where they originate from. And we can also, or my colleagues can measure where tips are located, where those filaments branch, and then measure the total hyphal length and so on. And that is all information that would be basically inaccessible using only two-dimensional imaging. And yeah, and another application that we have is spray coating of sugar spheres, which you can see here on the left, which is just a slice in a three-dimensional image, and then we can segment the hull and measure, for example, its thickness over the orientation, and then can also detect locations where the hull is delaminated from the particle. And this has then very important implications for the quality of the spray coating process. So this kind of highlights that this is not only applicable to crystals, but I will be talking about crystallization process analysis today, because that was my PhD topic. And the goal of my PhD was to use these three-dimensional methods for process analysis. And we used an exemplary seeded batch crystallization for that. And we calculated that we would need about 1,000 crystals per sample. And that was already a huge challenge, because before we only looked at single crystals to develop our methods. And yeah, so that, and obviously we can't place single crystals in the CT because a measurement takes like half an hour to 1 hour maybe. And then this would of course be a time limiting thing here. So our process looked like that we seeded crystals in the beginning, then applied a linear temperature ramp. And in blue, we can see here the corresponding saturation concentration, and the dotted lines with the axis is the actual concentration. So we can see that crystallization is happening here. And then we took samples every 30 minutes. So at 0 minutes, we had the seeds, and then 30 minutes, 60 minutes, and so on. And then the method that we came up with to actually be able to analyze such high numbers of crystals was that we printed such three-dimensional scaffolds in which we sorted single crystals. So in each cavity here, we sorted one crystal, thanks to my students. And then we were able to include about 800 crystals per micro CT scan. And with that, we analyzed 11,000 crystals. And the great thing about this method compared to just measuring them in bulk is that we can be sure that if crystals touch each other, they are actually agglomerates and not just crystals that touched in bulk. That would be very hard to segment, especially if the size distributions become a bit wider. And this is how an image looks like. So we see all these crystals nicely distributed in space, so we can take single crystals and analyze them and do our process analysis with that. The first information that we get from that, and we don't need any modeling, shape assumptions or anything for that, we just need those three-dimensional images. We can measure the surface area distribution and the volume distributions. And that is already great because both are very important for the mass balances. And that is because crystal growth is a surface reaction, and therefore we need the surface area to be able to calculate how the volume changes. That is great, but we were more interested in the shape of the particles. And we expected that all crystals should be octahedrons like this. And this is because we have a cubic unit cell here. And for this material system, we would expect all of the phases to be these 1-1-1 phases, and therefore they should all grow at the same rates, and therefore we should have these octahedrons here. But we saw that about 3/4 of the crystals were either flattened, elongated, or very weirdly shaped. And we also saw that these shapes transformed into each other. And we saw that irregular crystals become elongated, elongated ones become flattened, and flattened crystals become octahedron. And that is something we were able to explain, but we were not able to explain why such shapes existed. So we were able to explain why they transformed, but not why they exist. And our hypothesis at that point was that we knew we had damaged seed material, and that was just the material that we bought and sieved and used as seeds, and there were basically broken, damaged crystals. So the next step was that we asked the question, how do damaged crystals grow? And that is also something we use micro-CT for, and we glued damaged crystals, aberrated round crystals, as you see here in the top schematically, and as a picture here. We glued them to such growth racks, and then we were able to take three-dimensional images of these crystals that are now fixed and place them in a reactor, and then take an image again and repeat that cycle until we had a series of three-dimensional images that show the same crystals, but at different stages of their growth. So we can see here that a crystal is initially round and then through growth becomes faceted. And that is a qualitative description. We were also, of course, interested in a quantitative description. And for that, we overlaid we overlaid images. And this is what we can see here in red, which is a later time point, and in blue, an earlier time point. And then schematically, we can measure the distance of these two surfaces in many different directions. And then we can divide that distance by a time and get a growth rate. And now we can describe each point on the surface by its normal vector. So we can describe the orientation of the surface. And this normal vector can be described by spherical coordinates. So I guess that is kind of a known concept, but we have two angles here, an elevation angle and an azimuthal angle, and these two describe that orientation of the vector. And we can think of our crystals as a globe that can be unfolded to a map. And this is exactly what we did here. We unfolded the surface of our crystals to a map and can now display the growth rate depending on orientation of the surface. And then we can see, which is very interesting, that we get a symmetrical image here, which is kind of what you would expect because of the cubic unit cell. But we also saw that the minima here are exactly the phases that we observe in crystals. So we can use that information, these growth rates, for a new growth model that we can use for non-faceted crystals. So we can now simulate how non-faceted round crystals grow. And you can see those minima here that are the orientation of these minima that are here displayed as dots in that image are those light blue teal regions here of that crystal, and the rest is blue. And we can now see that if the crystal grows, all of that crystal becomes faceted, and basically the shape is defined by these minima here. And this description is not only qualitative, but also quantitatively correct. We can describe the volume evolution of these crystals and also the shape evolution. And we can now use that, go back to our previous study and look at how would such seeds grow. And we took different seed material or different crystals that we found in our previous study and saw that if they grow, we have weirdly shaped initial shapes. Then we also get shapes that are faceted in the end, but have not the octahedral shape. And this is just another example here where we have something that is kind of elongated and also get an elongated shape in the end. So the shape of the crystal here, of the crystals in a process, will very much depend on the seeds that we give, that we add to the process. And that brings me to my conclusion. I hope that I could convince you that three-dimensional imaging is a very powerful tool for particle analysis. We can get volume and surface area distributions without any need for any shape modeling or any advanced methods, but we can also use very complex advanced analysis methods to for example, extract hyperlength distributions from such fungal pellets, determine coating efficiency and also identify crystal phases in even such complex shapes as this agglomerate here. And then we can also use our methods for kinetic analysis and multidimensional modeling. And this helps us to understand very complex process behavior. And we can use this to parameterize, for example, population balance modeling, which we can use on a process scale. This is just another paper that we wrote on that topic, but this is not about particle characterization. So I didn't include that here. And with that, I would like to conclude my talk. And thank you very much for your attention.
Yeah, thank you, Simon, for your very nice presentation. Very interesting. As mentioned before, there won't be any possibility to ask questions. Now I am having a look to my chat room and there are no questions yet, which allows us for moving forward to our next speaker, who will be Sebastian Maass from Berlin. And Sebastian is a very active member of our particle systems characterization working party, which we introduced shortly before. And Sebastian is together with Stephen Ward-Smith, whom you will listen to a couple of minutes later, who just joined. Welcome, Stephen. And myself, we are chairing this working party. So if you feel interested in the topics presented there, don't hesitate to join us. Sebastian, are you there? I don't see your face yet. I see your presentation.
Yes,
the floor is yours.
I hope you can hear me.
Perfectly well.
Thank you for the introduction. And today I'm going to talk about challenges and possibilities of using inline image analysis. I think the presentation we had here from Simone was already a great motivation. Of course, this 3D analysis is cutting edge technology where you are thinking about how we move forward. Today, I want to focus more on industrial applications, so something what is production ready. And so this is what I'm going to show in my presentation. So I'm motivated what we are doing, give an introduction into the measurement equipment we're using, and give you some challenges and also some success stories in crystallization in different industrial applications. So from concept, we do have a batch crystallization. Would also work in a continuous crystallization, but I think the batch crystallization are a little bit more challenging for the image analysis, where you have the crystals grow over time, and then you take images inline with an inline microscope, and then you do need a powerful image analysis software to create some numbers. For me as a chemical engineer, to be able to optimize the process, I do need solid numbers to do this. So this is the whole concept, because we want to do feedback control. We want to make processes stable. We want to make them run smooth, and we want to save energy, time, and resources. And for that, we're using an inline microscope, as already mentioned. Many of the applications involve organic solvents, and therefore we do need an inline system which will work also under explosive atmospheres. So this is what we do have, an inline microscope available with different magnifications for different size ranges. Furthermore, not only the equipment itself is important, but also how you bring it into the process. If you want to track industrial crystallization processes, you do need to fulfill the requirements of very different customer needs, and so it should be available with different process flanges, process connectors. And then also very important, what is a challenge in many of the industrial applications is fouling. So you can only analyze clear images if you get clear images. If you are confronted with fouling, you do need the help of somehow cleaning the probe. We work together with a company here from Politecnico, and they do have a fully automated cleaning system where the inline microscope is retracted, and then you bring it after a full cleaning circle, dried and clean back into the process, so that you make sure you have stable readings throughout the whole batch crystallization. So that's the cooperation here between the Sopat and Knick here in Berlin. So this is the hardware. This is, of course, the first step if you want to analyze crystals with all these interesting shapes we already discussed in the first presentation. You do need to get good images, and then the next challenge, of course, is to analyze those images. And computer vision is a science on its own. Many aspects are moving there, and the Sopat software we are using for the crystal analysis is able to combine different algorithms, different libraries, classic approaches, but also like new approaches using artificial intelligence, neural networks, all these things. I think what is very important is that the system we are using is modular, so that you have an unlimited opportunity, or you have unlimited possibilities of combining different algorithms and different methods. And with that, we do get then, of course, only a 2D information. We already discussed that crystals are three-dimensional objects, but of course, opposed to many other characterization technologies, like the very traditional sieving, but also laser diffraction or laser backscattering, which are pretty distributed in the industry. They are all one-dimensional technologies, and with the image analysis, you are able to add a second dimension. With this second dimension, you get much more information. You're not only having size, a chord length, but you get different particle sizes, different particle lengths, and then also some shape information like the circularity or the aspect ratio. And this is clearly defined in the ISO standards, how to calculate those values. This is what you then get from the image analysis. And furthermore, the image itself contains integral information, because the whole swarm of particles, crystals, bubbles, whatever is in the image is, of course, a carrier of information. And so with this cumulative information in the image, you can do additional data analysis and then track this parallel, for example, to the particle size distribution, to the crystal size distribution you are already analyzing. So for example, big industrial processes, they do have bubble swarms in it. And these are things we can detect with image analysis, and then we can differentiate different kinds of particles in such a big process. To a degree, there we are able, based on the integral information in the images, to correlate it to concentration. Like the Lambert-Beer law, for example, there's a combination between the concentration and then the light intensity. So there's a lot of information in images available, but we need to make sure that, of course, we do use the right conclusions based on the information. So I already discussed that we do need good images. If you are a photographer, you do know that most of the challenges taking a good image is illumination. So if you have a typical API crystallization, like here, there you have needles, but you don't want the needle-shaped the needle-shaped crystals. You do a dissolution, and then you recrystallize the particles again to get the preferred shape. A lot of the quality of the images is depending on the illumination. So that is definitely one of the challenges. And here's another example from an industrial crystallization. So that's an organic fat, and over time we want to crystallize and then separate the particles, but because the concentration is changing, as well as the size of the particles is changing and the color is changing, so do the reflection properties. And with that, you have to adapt the illumination. And so that is one of the first challenges I wanted to talk here. So what we're using is different kinds of illumination. You do know them from standard microscopy. On the left, you do see a very typical example. This is reflection. So the camera and the light source are at the same, come from the same direction. So the information you're getting back to the sensor is the reflected light. If you want to add more illumination angles, you can use reflectors. We do use different ones, as you can see in the two middle images. We do direct reflection and diffuse transflection. So using a reflector there to add additional background illumination will create different kind of illumination. And then what is also very, very common in standard microscopy is transmission. So where the illumination comes from the background and the camera sensor is on the upper side. So you're getting a lot of shadow information from the particles. They all have advantages and disadvantages. On this slide, just using one example here, the direct transflection shows you already how you significantly influence the quality of the image by using different illumination options. Here we're decreasing the gap. Of course, with decreasing the gap, we're decreasing the volume which is in front of the probe. And by that, we're more or less decreasing the volume which will be analyzed or which will be shined through with the light. The smaller the volume, the higher the contrast. But as a chemical engineer, I'm of course very much concerned about small gaps, because this is exactly where fouling could happen very easily. And that's why this solution with the transflector is working in industrial crystallization, but usually we do need to combine it then with an automated cleaning system so that we make sure we're really measuring fresh crystals and nothing what is growing in front of the what is sticking in front of the lens. Another example here, just to see the influence, this is transmission, where we do get a needle crystallization. The needles are getting illuminated from the back, making them dark on the image, and then we are able to analyze them. Of course, if we have solved the first challenge, means we have very good and clear images, and you as a human think I clearly can differentiate the different kind of crystals on those images. Then now the next challenge is, of course, to get them analyzed clearly. As already mentioned, computer vision is a science on its own. A lot of different approaches and a lot of different developments happening right now. And we're using a lot of them, but there are some, like, so to say, traditional approaches which are basically based on thresholding, watershed segmentation, for example, pattern matching, Huff transformation. They are generic approaches, traditional approaches, where you have to influence and optimize the parameters for the image analyzers once, and then you can use it. This is usually quite fast in adaptation, but it is usually very inflexible. So if some of the optical properties are changing already, you will get a lot of problems, misreadings in the quality of the signal. The second opportunity is based on neural networks, but as you can see here from my motivation image, especially the training of those algorithms feels like prisoner work, because it's very, very manual, very time intense. And so, but both of them are available. I could give a whole presentation just on the challenges. As we're here having spotlights, I just wanted to mention those are the challenges. If you solve them, you get very, very good results. You can differentiate between the maximum and the minimum size distribution. So the needles are clearly able to be identified, and then you can see how the particles are growing over time. Here on the left diagram, you have the diameter on the left over time and the number of particles on the right. The yellow line is the number of particles. As the particles are growing, the total number of particles per data point is decreasing, and the size of, or the length, as you can see here, the maximum Ferré diameter is increasing, the minimum Ferré diameter is decreasing. And here you can see the same in terms of the shape information from the beginning to the end. So this is just one example installation, successful installation example. And with inline images, we're able to give you a lot of information for smart process control. But typical challenge is, first of all, you need to make sure you have high image quality. And then if you achieve that goal of high image quality, you are now confronted with the next challenge: find the right image analysis algorithm. Many of them are there. We're working on AI algorithms. These approaches enable very robust analysis, but especially the training right now, it takes a lot of time. Next steps in our development is to automate the training using other AI approaches, also even for the training. Thank you very much.
Thank you very much, Sebastian. We are almost on time, and we truly appreciate this very nice presentation. And I hear that there are already plenty of questions arising, and please, for the next presentations also, please note to whom you would like to ask your question. So the dear audience, please note to whom these questions are directed, and Martin Pux, who's sitting in the control room, let's say, is directing these questions to the speakers. So again, thank you very much, Sebastian. The next speaker is Elena from Torino, and I'm waiting for her slides to appear on our screens.
Yeah, can you hear me?
Yeah, perfectly well.
Okay, let's see if I can share the slides. Okay.
Yeah. Elena, the floor is yours.
Thank you. Thanks, everyone. And thank you for inviting me to this, this webinar. So I think what I would like to talk about is multi-phase formulation, which is something that I've been working on for a few years, I think. But I want to approach this topic from a monitoring and characterization perspective, which I think fits with the scope of this event. So first of all, I'm going to talk about multi-phase formulations and how crystal engineering is related to this. And then I'll show you a case study of a material that we worked on for quite a long time. So oleofoams are is a dispersion of bubbles which are stabilized by solid crystals in an oil. And I'm going to show you a couple of tools and methods that we developed to monitor the production process and to characterize the product. And then I'm going to just show you some further work and conclusion. Sorry, I'm just having a bit of an issue. Okay. So first of all, why multi-phase formulation? For multi-phase formulation, I mean emulsions or foams, so materials that are made of different phases, at least two, but even three in the case of emulsions and foam, which are stabilized by solid particles. They are very interesting material for food, cosmetic and pharmaceutical application. I think the main issue with these materials is that they are thermodynamically unstable, so they can be stabilized using surfactants, which is the typical way of stabilizing this material, or we can use solid particles and crystalline particles in particular. And this is the so-called Pickering effect. If we look at the free energy to desorb a particle, a Pickering particle from an interface, this is related to the interfacial tension, the size of the particles, and the three-phase contact angle. So those properties, if you have a crystalline particle, especially the size, and in some ways the contact angle, they can be controlled via controlling the crystalline, the crystallization process and the crystal properties. So size, of course, we can grow smaller or larger particle, and while for the contact angle, we can play with polymorphism, we can play with habit in order to tailor the surface properties of these materials. Oleoforms are a dispersion of air bubbles in an oil phase. In this case, the material that we worked with was sunflower oil, and we use cocoa butter crystals to stabilize those forms. So in order to make this material, we first have to prepare an oleogel, which is a dispersion of cocoa butter crystal in the oil, and then incorporate air bubbles via aeration. Those are very interesting material, especially for food. So we can incorporate air bubbles in food and make low-calorie food. And also these foams, they have quite interesting biological properties, so they are quite interesting, especially for cosmetic application or for topical delivery of API. Now, in order to, one thing that we needed to understand was the so-called process structure function relationship. So to understand how the properties of the material in terms of stability and functionality were related to processing conditions. So we needed tools that enable us to monitor crystallization and also to monitor and characterize the final material. So in terms of the oleogel crystallization, so cocoa butter crystals that form in an oil matrix, they have a specific crystal structure. So this can be monitored, for example, via X-ray, and it can be done offline, or if you can do some experiments at small scale and monitor the process online. What we found was that during the oleogel crystallization, we were consistently making, even via changing some of the crystallization conditions. So, for example, the concentration of cocoa butter and the cooling rate, we were always making the same polymorphs. And the morphology of the crystal was, so cocoa butter crystal, they form nanoplatelets that then tends to aggregate in this material. And we could play with the crystallization condition, especially the cooling rate, to change the size of these aggregates. What we found was that the cocoa butter concentration was the main parameter that drives the properties of this material. However, it was a bit challenging to monitor the crystallization online of oleogels, because those are very opaque material. So laser backscattering technique were not that useful. With Raman, we had problem of fluorescence. So what we did is we tried something different, and we tried acoustic spectroscopy. Acoustic, so sound is an oscillation of pressure, so that is transmitted to a medium. Now, the speed of sound, the attenuation of sound is strongly dependent on the properties of the medium. So by measuring some of the acoustic properties, we can get information on the system. We can use continuous waves, but in the case of the work that I'm going to show you, we use pulses. So what we did is we developed a probe using a commercial transducer, and this is a reflection probe. So we had a mirror at the end to monitor crystallization. The probe was very simple, and it could be immersed in a crystallizer in order to collect data during the crystallization of the oleogel. What we needed was a source of pulse and then an oscilloscope to read the data. The type of signal that we got from a probe is like this. So we have, as I said, we have a transducer. Then we have the sample, and between the transducer and the sample, we have a buffer rod, which is basically a cylinder of polymeric material where sound is reflected. So the signal that we see here is the first reflection inside the buffer rod, and then the sample. This first reflection is quite useful because we can use it to normalize the sample signal for temperature, because acoustic signal depends on temperature as well. So we built the hardware, and then we developed all the software on MATLAB. And then we used the tool to look at crystallization of oleogel. So here you can see just the speed of sound, so this red trace, and then the attenuation, which is the green trace. So the attenuation, we compare the signal with the standard turbidity probe. The attenuation signal was pretty much in agreement with the light transmission and light absorbance, while with the speed of sound, we have, of course, the effect of temperature. So we can see the signal changing with temperature, and then a sort of jump when we have the nucleation. One thing that we noticed is that with the turbidity, we could see some changes at the very beginning of the process, which are probably related to a polymorphic transformation that we couldn't see with the acoustic signal. And this probably means that this tool perhaps is not good enough for monitoring polymorphic transformation. What we decided to do is, so we could use just the speed of sound and the attenuation, or we could use the whole pulse wave, and then some machine learning algorithm in order to get qualitative information of the system. In particular, what we could get was the solid fat content during crystallization, so the amount of crystals that were formed. And we applied very standard machine learning algorithm to try and relate the acoustic signal with the solid fat content of the oleogel, which is a function, as you can see here, of the temperature and the concentration of cocoa butter. What we noticed is that non-linear models were better than the linear one. And perhaps this is not surprising, but we found models that fit the solid fat content quite nicely. And we used this tool, so we validated the machine learning algorithm through several experiments, and we found very good agreement with offline characterization done with solid state NMR. So this was a quite in-house built tool that could be used to monitor oleogel crystallization processes. After the formation of the oleogel, what we do to form an oleofoam is we just whip the material using a kitchen whipper. In this case, we needed to use a jacketed bowl to keep the material cold while whipping, and we get a very thick foam very opaque foam. And even in this case, traditional characterization techniques are not very useful. So what we needed to do was to try something different, and we decided to go with X-ray tomography. So we use X-ray tomography to look at the bubble size distribution and the structure of these materials. We could monitor the aeration process, so the bubble size distribution during the aeration process, and maybe from the 3D rendering we don't see much, but we could get size distribution of the bubble with this technique, and we could monitor the differences between different formulations. And also, for example, we could look at sphericity of the bubble, which tells us how the crystals are interacting with the bubble itself. Another thing that we looked at was the effect of storage on the structure. So we can see clearly Oswald ripening and a separation of the two phases, the air and the oil. And again, we look at different formulation, and we found that the more the crystal, the more stable was the material. And finally, I think that we looked at was thermal destabilization of those materials. So we heated the foam up, and then we look at how bubbles were coalescing and basically separating from the material. And this tells us, for example, how this material would behave after ingestion or after administration for topical delivery, for example. Those were dynamic experiments. So what we could do is we could take radiography rather than tomography. And this is an example where we could see the dynamic of, in this case, this was coalescence of bubbles. So this is, in conclusion, I just show you some technique. So an acoustic probe to monitor ology crystallization, and then how we can use 3D tomography to look at the structure of this case study for a multi-phase formulation. And I think my approach is that the more complex becomes the material and the more technique we have to use, and perhaps going a bit away from the traditional techniques for crystallization. I think this is the end of my presentation, so let me just acknowledge the funders, the collaborators, and of course you for your attention. And happy to answer any question, I believe, on the chat.
Yeah, thank you, Elena. Thank you very much for this very nice and deep presentation. As you mentioned, there is room for questions and your answers then after our session and directly via the chat room. Just don't forget to mention that your question in this case regards the presentation of Elena. Thank you very much. The next speaker comes from Manchester, will be Ashwin. Can you please? Yeah.
All right. So is it
very
fine?
Good. The floor is yours. Go ahead.
All right. Yeah. Thank you very much. So this talk is going to be on accurate characterization of size and shape of crystalline powders. Sorry, I don't know why my pointer is not working. Let's see if it does. No, it doesn't. All right. Sorry about that. Okay. All right, yeah. So the prerequisite is that we agree that crystal size and shape has an impact on production of powders, okay? Note that there will be a number of QR codes that will pop up throughout the presentation, so please have your scanners ready. Okay, so why is size and shape characterization important? Well, it's one of the key descriptors for the solid powders that we usually encounter in crystallization process. So if you have a good size and shape characterization, then what you can do is you can build nice process models that can basically describe the evolution of a given crystallization process. Then, of course, if you have a good characterization, you know what is happening inside your process, so you can go ahead and then design better processes and in turn also use them for controlling your crystallization process. Last but not the least, crystallization is never carried out in isolation. You always have filtration, washing, drying. If you're dealing with things like pharmaceuticals, you also do things like tableting the particles and so on, right? So having a good characterization also enables you to engineer better downstream processes in terms of all these operations.
Ashwin, sorry for the interruption. There seems to be a problem with the sharing of the screen.
Is that so?
Yeah, we saw the slides in the very beginning, but now I think most of the speakers are not able to see them.
All right, let me check it again. I don't know what so give me a second. How about now?
Yeah, now we can see the screen. Try to.
Is it fine?
Presentation. Yeah, part of the presentation is cut out. Maybe you can, if that's a PDF file, you can share it without the presentation mode.
Is the whole thing cut out, or do you see it now?
No, just a tiny part on the very last right part of the slide.
Oh.
So we can also go on like that.
Okay, yeah. Sorry about that. I don't know what happened.
That's okay, no worries.
Yeah. Okay. Okay, so let me quickly show you what I showed here. So I was just trying to talk about the different uses of size and shape characterization. So it will be used for process modeling, process design and control, and engineering downstream processes. Okay, so over the course of this presentation, I would like to make a couple of remarks, and this is my very first remark. Given the importance of accurate having a good size and shape characterization, the expectation, as always, for all of us is to get an accurate size and shape characterization. Well, how does this translate to? If you have a faceted crystal that pretty much looks like this, you can have a polytopic representation of this particle so that you can describe it very accurately, but it's computationally expensive. So maybe we can assume this to be a sphere. In which case you basically have a generic particle model, and this can be an equine-shaped particle. We can do the same thing for elongated particles, where you can assume these particles to be a cylinder. In the case of plate-like particles, you can assume these to be a cuboidal one. But the reality, unfortunately, is that we end up assuming in most cases everything to be a sphere, right? So this would mean your approximation of the particle shapes pretty much looks like this. Spoiler, this always doesn't work. It's valid in most of the cases when you have equine-shaped crystals, or if you have crystals at steady state shape. So if you want to know more about this, feel free to go and have a look at this paper that I have referred here. Okay, so now that we know that there's a problem, we need to address it one way or the other, right? So before we go ahead and start addressing this problem, we have to first see how we can quantify size and shape. So if you have an equine-shaped particle, right? So where you characterize your particles using a single characteristic length, this is your familiar one-dimensional particle size distribution. So you basically have the number density as a function of the particle length. The moment you go for elongated particles, which are, let's say, characterized using a cylinder where you have a given length and a given width, you have a three-dimensional plot here. So you basically have the number density as a function of the length of the particle and the width of the particle. For better visualization, we can always look at a contour plot, which will help us track the process in a much, let's say, friendly way. When we go to 3D PSSTs, we have the length, the width, and the thickness of the particle. So we live in a 3D world, so we cannot visualize a 4D plot. So what we end up doing is instead is that we use isosurfaces, and this is basically how a 3D particle size and shape distribution would look like. Now, we have ways to quantify it, but how is it typically done? So if you look at the equine-shaped particles, I mean, we have a number of devices that are considered to be industry standard. For instance, we have the laser diffraction, the FBRM, the PBM, blaze matrix, Coulter counter, and so on, which have been used for monitoring, modeling, and quality control purposes. If you move to elongated particles, well, these are advanced devices in the industry used for research and development primarily, and these can be things like single or dual projection imaging, like the morphology, the Sopat, the PBM, the blaze matrix. Some of these we have seen during the course of this webinar. If we move more towards the platelet, or let's say a more complicated sort of characterization, these are typically advanced devices in the academia. So these include things like single or dual projection imaging and a computer tomography, like the one that Simone showed at the beginning of this webinar, right? And during this talk, my focus will be on the latter two aspects of size and shape characterization. And this is basically our take on how we have tried to solve it. Okay, so this has been a work that was conducted both at ETH Zurich in Switzerland and also here at the University of Manchester. So I'm going to show you a couple of devices. The first device is what I call as the petroscope, and the second one is what I call as the disco. Okay, so let's get started with the petroscope. So this device is basically an offline imaging technique. So how does it work conceptually? Well, you have particles that are basically dispersed on a substrate. You take a camera and then you try to get the projection of these particles. You let these projections go through an image analysis routine and you extract the length and the width of the particle. How does it look in reality? As I had said, you have not one particle, but you have a number of particles that are basically dispersed on a substrate, placed on a moving XY stage. And this is an offline characterization technique. Your particles lie flat on the surface, so your measurement is typically not affected by the orientation of these particles. Okay. Then you take images using a camera plus a lens system, and you go through with your image analysis routine. Okay. So this is just an example of how it might look like. So here you have ascorbic acid crystal, which is around 60 to 70 micrometers in let's say in length. The second panel basically shows you the 2D projection after we have gone through the image processing step. And if you repeat this step for countless number of particles, then you basically get a two-dimensional particle size and shape distribution. To basically get the length and the width of the particle in a simple way, you can just fit a bounding box around it, and then you can find the length and the width. Okay. So now that we have a two-dimensional particle size and shape distribution, well, the obvious question would be, okay, we also have a third dimension that we need to characterize, right, which is the length. Conceptually speaking, what you can do is that if you have some sort of height sensor, you can profile the surface at different points. And what you can try to do is to get the distance of the surface to the sensor across the whole particle. You can average it out to get a rough estimate of your thickness of the particle, right? How have we done it? Well, we have done it by using what is called as a chromatic confocal sensor, which precisely does what I just mentioned. So it basically scans over the particle, and you can basically get the height of the crystals. Going back to the example that I showed before of the ascorbic acid case, since we have an additional sensor that also gives us the height information, we don't have a 2D projection anymore, but we have a 3D reconstruction of the particle, right? So you already see that the bottom one was what you got when you just had the camera, and the top one is basically what you get when you have a reconstructed crystal using both the sensors, right? And since we have information coming from the length, width, and the thickness, you don't have a 2D particle size and shape distribution, but you actually have a 3D particle size and shape distribution. Okay, so what you see in the center is basically a blob of the 3D particle size and shape distribution, and its projections on the three planes that you see are the 2D marginal distributions. Okay, so this is basically one technique that we have developed, which is completely offline. You disperse the powder on a plate, you image them, you use the confocal to get the height, and in turn, you will end up getting your 3D particle size and shape distributions. But well, offline might not always be the best case or the best option that you have. So you might want to also start considering things like online projection, where you can actually track the process in real time. And this is where the disco comes into play. And online characterization brings its own set of challenges, as we'll see now. Okay. So what basically happens is that you have a particle that is in flow because you have particles suspended in a solvent. Okay. And you can do the same thing that we did with the offline part. You can install a camera, and then you can look at the projections. You can obtain the length and the width of the particle. Now, the moment I change the position of the camera, what you will see is that your projection of the same particle would look completely different. So if you try to extract your length and width of the particles, it'll actually be very, very different to what you had with a camera in another position. So this is something that we might experience when we watch a 3D movie. Basically, we use a couple of these projections to reconstruct a 3D image of the particle, right? So that's basically the green box that you see here. It aligns very well with the red particle that you have. So how did we do it in reality? Well, this is what we built a few years ago in Zurich. We basically have a crystallizer. We have the disco over here. The crystals are suspended in a solvent or an anti-solvent. You pump them through a flow channel. They get imaged using these two cameras, and then it's pumped back into the crystallizer again. At the core of this device is basically a comprehensive shape analysis pipeline that runs in real time, where it converts thousands of images to particle size and shape distributions. Okay, so this is just an example of how growth of an ensemble of elongated crystals would actually look like in reality, right? So on the left-hand side, you see the evolution of the 2D particle size and shape distribution. On the right-hand side, you will see the evolution of the average length and the width of the particles, okay? As expected, since you're growing the crystals, your length and the width of the particles are increasing. And if you look at the left-hand panel, you will also see the contour visualization of a particle size and shape distribution. The distribution moves towards the top right, indicating that you're actually growing the crystals. And keep in mind that the axis is actually quite different. So you have 600 over here and 100 over here, which indicates that the length is actually predominantly bigger when compared to the width of the particle. Okay, so this was all fine, looks very nice, right? But then let's make it a bit more complicated. We have the same particle, let's rotate it a little bit. Okay, so it's the same particle, it's in flow, we have just rotated it by a given angle. So what you already see is the projection is different. Since the projection is different, the reconstruction is very, very different as well. So now you don't see a thin particle anymore, but then you see a chunky box that was reconstructed using these two projections. Now, this is usually a problem with in-flow images. So you basically have particle orientation that affects the quality of your final output. Okay, so basically we had to address this problem. We had to correct this error that arises. So one way of doing this would be to go and do a bunch of experiments and try to correct it by building a model. But then this is extremely laborious. So what we did was we took the disco, we built a digital twin of the disco, which we call the virtual test bench. All we do here is we virtually generate millions of particles with different sizes, shapes, and orientations. We extract certain key features from these images like contour areas, reconstructed particle volume, circularity, convexity. We feed everything through a neural network. We train the model, and what we end up getting is basically the length, the width, and the thickness of the particle that has been corrected for some of the errors that comes because of the orientation of these particles. Okay, very nice. So this was shown. It actually worked quite well, but this was all inside a computer, right? So we need to, of course, validate everything experimentally. But the challenge again is that there are no calibration standards that are actually available that we can use to experimentally validate these things. So what we had to do was we had to come up with our own calibration standards, for which we used photolithography. And what we ended up doing was we generated a bunch of populations of different sizes in terms of their length, in terms of their width, in terms of their thickness. So here, just as an example, the blue ones have a thickness of 33 micrometers, the red one 66, and the green ones 100 micrometers. Okay, so we did this. We have our disco. We put the neural network model inside, we took these populations, we fed them, we put them inside the crystallizer, and then we started analyzing these populations. Okay, so this is the calibration standard that we made. What you see here is just the mean length, and this is what was measured with the disco. So if you look at just a couple of quick things, so if you look at the width of the particle, it's around 100 micrometers, which is very well aligned with the calibration standard. The length of the particle is 100, 200, and 300, and it's something that you also see here when you compare it with the calibration standard. But then the thickness in the worst case scenario, which is actually what is shown here, is a bit off, but that is something that is also expected because you have small particles and the model inherently has an error. But we have tried it on many different populations, and what we have seen is that the ML model that we have developed has actually helped us reduce the error in estimating the lengths from 160% to 30%. And the remaining error that we have is simply because of the orientation of the particles that we actually cannot account for anymore. Okay, so what have we done with all of these things? We have used it to basically build 2D breakage models, 2D dissolution models. We have used it to develop multi-state cyclic processes for size and shape manipulation and for controlling these processes as well. Okay, and if you're interested in looking at more of the applications of these devices, there are a bunch of contributions from Anna, Daniel, and Petros, who are also the co-authors of this work at Isaac in Glasgow in September. Okay, so this is how it looks like in reality. On the top, you have the petroscope here at the University of Manchester. In the bottom, we have a couple of discos. We are currently building 3 more discos in Switzerland and the UK. So if you want to test the potential of these devices for your applications, feel free to send us your samples, or we can also discuss about having these devices in your lab. So if you want to have a chat, I'm more than happy to do that. Okay, so I'm coming towards the end of my presentation. I said I'll make a couple of remarks, and this is my second remark. Okay, the expectation is that we would like to get similar particle size distribution with different techniques. Okay, so what you see here is basically a cumulative distribution. So it's not a normal particle size distribution, but then I've converted it into a cumulative distribution. This is a real population. And if we try to compare the measurement that we get from the petroscope and the disco, which are the two devices that I showed during the course of this presentation, they match quite well. But the reality is, well, it really depends on the kind of devices that you use. What you see here is basically comparing the measurement that we got from the disco and the petroscope with two commercial devices that are actually currently used widely, okay? And you can already see that the commercial devices themselves don't agree well with each other. And also they are quite different to what disco and the petroscope basically gives you, okay? So this is something that I want all of you to keep in mind, that we might have these challenges, and this is something that we have to seriously think about. And it goes without saying that there are only a handful of devices that can give you 2D particle size and shape distributions, and 3D is an even more complicated problem. And again, the disco and the petroscope basically gives you very similar measurements. Okay, so my take-home message is pretty straightforward. Accurate size and shape characterization is tough. Challenges exist. So as a community, we must invest and exchange resources on size and shape characterization and standardize our measurement protocols. And I should, of course, make a disclaimer that there are many more issues, but these are the points that basically fall within the scope of this webinar. Okay, thank you very much.
Thank you, Ashwin, for the presentation. We are running 6 minutes late, so I'm gonna hand it over to the next speaker, Bukar Eral, from Technical University of Delft in the Netherlands.
Yes. Thank you very much, Daniele.
Sure. Try to share the screen and let's make sure that everything is working properly.
Yes. So can everyone see my presentation in?
Yeah, I think so. Try to move to the next slide.
Okay, so let's try.
Yeah,
and even the movie is working. Okay,
yeah.
So that's very nice.
Yeah,
Thank you very much, Daniele. So my name is Burak Eral from Technical University of Delft. And today I'll be talking about our efforts to contribute to an interesting scientific problem. This problem is non-photochemical laser-induced nucleation. It's a problem and it's a challenge, if you will, and it's also an opportunity. In 1996, an interesting paper emerged that describes what you will see in the movie that I'm going to show you. So you see in your screens a potassium chloride solution that is slightly supersaturated. So if you don't disturb this solution, it takes weeks to a month to crystallize. But now I will activate the movie, and you will see that there's going to be a laser beam passing through the solution. It's a nanosecond beam, so you will not see the beam, but you will see the reflections coming from the beam. And after that, you will observe something, and then we'll go further. So you see the reflections coming from the beam. That is the cell phone of the master student, the pixels of the cell phone of the master student dying at the moment. But when the camera approaches, you see a rain of crystals. So this is a non-photochemical laser-induced nucleation. That in the literature, there are over 40 different compounds that have been reported to show non-photochemical laser-induced nucleation. Yet we still do not understand how it works. What I mean by that is we do not know the underlying mechanism. Of course, there has been various mechanisms that have been proposed in the literature. The first proposed mechanism is called the optical Kerr effect, that suggests that the electric field of the laser biases the solute molecules, which decreases the activation free energy for nucleation. Unfortunately, this method, this hypothesis, does not explain all observations, particularly the empyrean activity of of simple salts such as metal halides. To explain the ambient activity of metal halides, isotropic electronic polarization have been proposed that assumes that due to the different dielectric constants of the solute and the solvent, there is a gain in free energy. Unfortunately, this method, this hypothesis also does not explain the ambient activity of gases, and it also does not explain very important observation in the ambient literature, that is to say, there is a threshold below which ambient does not happen. To basically move forward with the third hypothesis that was proposed to explain the drawbacks of the first two hypotheses is the cavitation heating of the impurities. So this mechanism assumes that there are impurities such as nanoparticles, and these nanoparticles absorb the light and locally evaporate the solvent to trigger nucleation. And this mechanism has indirect evidence. That is to say, when you add nanoparticles into a supersaturated solution, and if you irradiate it with a femtosecond laser and a nanosecond laser, you get increased nucleation probabilities. But this particular hypothesis has no direct evidence yet. So then that's what we will be focusing on. So to start this project, we basically focused on first repeating the earlier ambient experiments, just like the one that you have seen. Then we built a microfluidic setup that allows us to get statistically significant number of experiments, identical experiments. In this setup, you have a droplet microfluidics. You expose the produced droplets with a laser beam, and you use machine learning algorithms to detect the crystals after this. And the third approach that we had is high-speed microscopy. So we wanted to look into time and length scales that are not accessible by bare eye, just like the ones that you have seen, just like the experiment that you have seen in the earlier video. So we have done two significant changes in the standard ambient setups. First, we took a sample holder that allows us to look into the system with a microscope. And we sealed the system with an oil. And then we added a ppm level impurity, potassium permanganate, into an aqueous KCl solution. And this is very important because that allows us to dictate how much energy, how much of the laser energy is absorbed by the solution. And I have to say that this is always a debated topic, because in NPLN, neither the solute nor the solvent has absorption bands at the irradiated frequency. And moreover, the laser intensity is considered to be low to trigger photochemical reactions, therefore the name non-photochemical laser-induced nucleation. So I will show you what we have seen with a standard camera. So something that is what you might have with your the cell phone camera, for instance. So this will be recorded at 50 frames, and this is what we have seen. We shot the laser, some disturbance happened, and the crystals formed right after that, seconds after that. And if we look into the still images, a time-lapse image, what you see is that initially there is nothing, of course. The laser is triggered, then you have a disturbance seconds after the crystals form. So this tells us that we have to look into something at between these the first two images. So we need to access milliseconds and the microsecond time scales. And to do this, we used high-speed microscopy. And when I mean high-speed microscopy, we're talking about million frames per second, and we are looking at micron scale. So, and to do this, we have to basically only limit ourselves to a narrow field of view, just like the one highlighted in the screen on the right-hand side. And this narrow view provides us microscale, microsecond accuracy. So what you see here is that first you see a dark contrast object appearing, and then that dark contrast object grows. And if you basically stitch these two images is a time-lapse image, what you see is there is an expanding bubble, and then this bubble then collapses. And seconds later, the crystals form. So then, of course, the question that might be in your mind now is, what does that bubble have to do with the emerging crystals? So, of course, to understand this, we need to first understand why the bubble forms, and why does it expand, and why does it collapse. Initially, at the laser spot, because we know the energy that we are supplying, we know how much of the energy is absorbed by the liquid. We know that we know the temperature of the liquid where at the laser spot. So what we do is the energy that we apply, it goes to evaporating the solvent. And then that at the focal point, the bubble is hot. And we know that when a gas is hot, it has high pressure from ideal gas law. So the bubble expands. As it expands, because it has more pressure than the atmospheric pressure, it starts cooling down. As it cools down, it collapses. Okay, so at this point, I have to tell you that, I have to remind you perhaps that potassium chloride has increasing solubility with temperature. Therefore, simply heating the solution would not trigger crystallization. As a matter of fact, it would stop crystallization from happening, as the supersaturation would be decreased. So the first thing that we did is we changed the laser energy and the bulk supersaturation, and we look at the probability of nucleation. What we have seen is that at higher laser intensities and higher bulk supersaturations, the nucleation probability increased. And we have seen the same trend with the number of crystals that are forming. Moreover, we observed that at higher laser intensities and bulk concentrations, more needle-shaped crystals form. And that is an indication that at higher supersaturations are created. And next, of course, we focused on the size of the bubble, dynamics of the bubble. What you see in your screens is on the y-axis, there is the diameter of the bubble. On the x-axis, there is the time. With increasing laser intensity, we have seen that bubble size increases, but also the bubbles survive for a longer amount of time. And of course, at this point, we know the dynamics of the bubble from the experiments. To get supersaturation, we need the concentration and the temperature. And to do this, we'll do finite element simulations. So just to briefly touch this, we will start by a Rayleigh-Placet equation. What it tells you is that as the pressure inside the bubble is high, that pressure is going to overwhelm the bulk pressure, the atmospheric pressure, Laplace pressure, and the viscous dissipation required to move the bubble. And then we have to, of course, look into the temperature of the surrounding liquid and the temperature of the bubble. So they will be in equilibrium, of course. And we have to model it as a spherical symmetric system. And what this tells us is that we assume that all the energy that is given by the laser has to be distributed to heat the gas inside the bubble and to evaporate the solvent. And eventually, of course, if the solvent has to evaporate from the liquid to the gas phase, we have to account for it. And this we do with the Hertz-Knudsen equation. And eventually we connect the pressure to the temperature and the mass of the vapor through the ideal gas law. So this allows us to predict how the size of the bubble changes with the laser energy that's provided. And this is very important because this allows us to basically ensure ourselves that we are on the right path and the concentration and the temperatures that we will predict are accurate. And of course, the next step is the concentration and the temperatures that we predict. What you see is with increasing laser intensities, the concentration first increases and decreases. And that is due to the fact that the bubble, the solvent evaporates into the bubble as it's expanding. And when it is cooling down, it condenses and decreases the concentration. And when you look into this tool, eventually this creates a microsecond regime where there is a supersaturated generated. And you see that that time available for the supersaturation increases with the increasing laser intensity. And with the last slide, I would like to show you that the experiments and the simulations that we have follow the same trend. And even a classic nucleation theory check gives us the right mean and right solid liquid surface tension. With this, I would like to finalize my presentation. And thank you very much for your attention.
Thank you very much. That was very interesting. Thank you again. So let's move on to the next speaker of the day, which is Vidit Tiwari from the University of Limerick in Ireland. I've noticed that Daniel Piri from ETH has shared with the audience a link from which Ashwin's slides can be downloaded. So since part of them were cut out, if you want, you can download them and browse through them, and maybe that will help you in formulating questions for Ashwin. Vidit, the stage is yours. Yeah, we do see your screen. Thank you. You also have 15 minutes.
Okay, so just give me a second. Hi, so I'm Vidit, and I'm working with Professor Vivek Ranade and Gavin Walker at the Bernal Institute in UL, University of Limerick. So today I'll be talking about my work on crystallization using fluidic devices without moving parts, which is part of my overall PhD work on continuous anti-solvent cavi crystallization. So that's a term that I'm coining over here, cavi crystallization. That's just crystallization intensified using hydrodynamic cavitation. So controlling the particle size distribution of pharmaceutical APIs during crystallization is one of the important design objectives to obtain high quality crystals, which have the desired critical quality attributes. So these critical quality attributes, such as the particle size distribution, affect the surface area to volume ratio of the particles, which in turn affect the bioavailability, dosage, flowability, compressibility, and many other properties. So the size distribution can be controlled either by controlling the supersaturation consuming steps of crystallization, which are nucleation and crystal growth, or there are several other methods, such as using, such as changing the entire crystallizer. So for example, using tubular reactors instead of conventional MSMPRs, or other fluidic devices, which could be static mixers or cavitating devices. Another method would be to use upstream processes such as ultrasound or high shear wet milling to induce nucleation, or even laser-induced cavitation, as Parag just showed us, or temperature cycling, feedback control. These can be used to control the particle size distribution. Apart from these, there are several processes which can be used for selective dissolution or particle breakage to control the size distribution. So ultrasound, high shear wet milling, dry milling, even hydrodynamic cavitation are some techniques which are used to break the particles. So as I previously said, one of the ways of controlling the PSD is to change the crystallizer entirely. And fluidic devices without moving parts are being investigated for this purpose for some time now. An ideal crystallizer would be one that provides good mixing, but also a very narrow residence time distribution, so that all the particles would experience the same amount of time in the supersaturation condition. So they would grow for the same amount of time, nucleate for the same amount of time, etc. So unfortunately, such ideal crystallizers are hard to come by. Mixing performance and residence time distribution, although can be tailored using a combination of these fluidic devices and different flow strategies, of course. So previously, colleagues of ours have shown the effect of using different fluidic devices on the particle size distribution in the anti-solvent crystallization of paracetamol. And they found that the particle size distribution becomes narrower and smaller. So I'll just highlight the figure over here. So the particle size distribution becomes narrower and smaller. So here the blue bars over here are the mean of the particle size distribution, and the orange bars you can see there are the standard deviations. So for using different fluidic devices, you can use by using different fluidic devices, you can reduce the mean and the standard deviation as well. So the two majorly two devices were investigated by our colleagues. One was the fluidic oscillator, which showed better mixing. I mean, it was because of the better mixing that the particle size reduced. And the other was the vortex-based hydrodynamic cavitation device called a vortex diode. So in the vortex diode, the smaller size was due to the breakage of particles due to hydrodynamic cavitation. So I will be focusing on hydrodynamic cavitation for some time now. So as you already saw in Burak's presentation, what cavitation is, it is this evaporation of liquid into its vapor surrounded by the liquid. So here in hydrodynamic cavitation, we cause cavitation by reducing the pressure inside the vessel. So as the pressure goes below the vapor pressure of the liquid, we see vapor cavities being formed, and as soon as they come back out of the vessel, the cavities collapse under the normal pressure conditions. So hydrodynamic cavitation allows generation of cavity collapse conditions similar to ultrasound, but at much lower energy inputs. And here we can use various cavitation devices like Venturi, orifice, or a liquid vessel hydrodynamic cavitation reactor. But these devices are linear flow devices, and there are some disadvantages to that. One of those is that the cavities are formed because of the pressure drop, and these pressure drop usually occurs around the walls of the device, such as in case of Venturi or orifice. So the cavities induced are induced around the walls, and they also collapse near to the wall. And we all know that cavitation causes material erosion in the vessel. So if the cavities are formed near the wall of the vessel, there will be material erosion and the vessel will be rendered useless after some time. But in a vortex-based cavitation device, the cavities are formed at the eye of the vortex over here, as you see. And these cavities are away from the wall of the vessel, and they also collapse away from the walls and in the center line of the vessel. So there is very less erosion. And also we have seen that for linear devices, the cavitation inception occurs in orders of, in pressures of orders of around 10 to the power 3 kilopascals. Whereas for vortex diode or any vortex-based cavitation device, I'd say, the cavity inception occurs at an order less than that, so around 100 kilopascals. And here we see the work of our colleagues where they have shown that using a stirred tank, just a simple stirred tank, the black curve over here that you see, that is the particle size distribution obtained from crystallization in a stirred tank. And adding a vortex diode to the stirred tank gives you a much narrower and smaller particle size distribution. So we also know that breakage and secondary nucleation are the dominant mechanisms in crystallization where cavitation is also occurring. Then we move on to the measurements techniques that we use. So we have been using some inline monitoring techniques for particle size distribution. Out of these, one of these is an offline method, which is the laser diffraction. And we use that to validate a mathematical model that we use to convert the chord line distributions that we get from an FVRM. So this model was developed by our colleagues, Pandit and Ranade. And such mathematical models have their limitations. So some cannot be used for needle-shaped particles because there are shape factors coming into a picture when the needle-shaped particles are crystallized. And most of these mathematical models that we use assume chords to be on a circular shape. So, and you may notice that we have different techniques for particle size distribution, since that is the critical quality attribute that most of our focus is on. So recently we have started using Sopat probes for inline imaging. So I'll take some time to talk about Sopat. Thankfully, Sebastian gave a great presentation explaining how this works. So for now, we have only verified Sopat measurements using paracetamol suspensions containing particles of known size, which was around 115 micron. So that's the sort of mean diameter I'm talking about, which was calculated using an FVRM. And this entire study was conducted on a solid fraction of 2%, which is, I know that it's less than what you would usually encounter in industrial crystallization processes. So the suspension was in similar stirring conditions that we encounter in our stirred tank crystallization experiments. We immersed an FVRM probe and a Sopat probe in the same suspension and measured the particle size distribution using both the techniques and got fairly similar PhDs. The slightly smaller value of the mean diameters for the Sopat compared to FVRM is could be because of the small artifacts that we see in some of the pictures over here. So I've circled some of those artifacts. So these artifacts are usually formed because of particles which are only partly in focus. So a portion of particles is out of the focus, and usually because of that we see only a part of the edge being detected because of the Sopat image analysis. So, but this difference will reduce. So this difference in the particle size between Sopat and FVRM or any other technique will reduce if the particle size of importance is the volume weighted particle size. Since the contribution of these small artifacts will be minimized on higher order weighting. The artifacts appear, well, I have already talked about the particles being not in focus. And also the effect of these artifacts can be minimized if the solid loading is high, which will be the case in some of our experiments where we work with very high supersaturation ratios. So I'm yet to try Sopat in an actual crystallization experiment where the PhD will be dynamic. So hopefully in later work, I'll be showing PhDs obtained through inline imaging. So, and we have also been working with APIs in our lab such as CBZ, carbamazepine, which form needle-shaped dihydride particles. And inline imaging can give more information on the shape of these particles compared to FVRM. The shape affects the CLD only when the aspect ratio of the particles is very large, or compared to laser diffraction, where a spherical particle assumption is imposed on the results. So we did some batch crystallization experiments in different mixing strategies, and also with by adding a cavitation device at the end. And by different mixing strategies, I mean, in one of the cases, we mixed the solvent and the anti-solvent directly inside the crystallizer. And in the other case, we mixed it in a stream which was looped back into the reactor. So in an external stream, the mixing occurred. And in the third case, again, the mixing occurred in the external stream, but there was a cavitation milling device. And I have mentioned that there are different energy dissipation occurring inside these three conditions. So in the cavitation case, the energy dissipation per unit volume is quite high, as you see. So we expect the best of mixing and even breakage to occur in this kind of case because of the turbulent motion inside the cavitation mill and also because of the collapse of cavitating bubbles. So here I've just mentioned that there are different mode of additions that I've used. So whether I add the solvent into the anti-solvent or the anti-solvent into the solvent. So I've changed the mode of addition, supersaturation ratios, and added a cavitating device. And we also did a continuous crystallization experiment to see the effect on the yield and productivity. That's probably not useful to the topic that we're discussing here. So here all the measurements are taken using an FVRM since we are yet to figure out how to use Sopat in our lab for continuous experiments. However, we hope to improve upon it in the future using inline imaging. So mixing, as we see here, at different scales can affect the particle size distribution significantly. So this is a case where reverse and direct additions are investigated. And the mixing occurred inside the stirred tank reactor, whether it's the anti-solvent being added or the solvent. So it's added directly into the stirred tank. And we saw the mode of addition had no effect on the pHD, which suggests that there is very poor micromixing inside the stirred tank, which results in similar local supersaturation in the stirred tank in both the cases. So we see that the mean and the standard deviation for both the cases is same, even though the mode of addition is different, which is surprising for us because usually in most of the studies that we see, people report that adding the solvent into the anti-solvent would result in very high local supersaturations. But that will only occur when you have a very good micromixing inside your stirred tank. Then we added, so we did another experiment with reverse adding, which was the adding solvent into the anti-solvent. And we just changed the supersaturation ratio this time. And we see that the particle size is even larger now. And this is because the mixing condition in the reactor may correspond to low micromixing and high macromixing, which would mean that there is supersaturation available for growth almost everywhere in the reactor, even though nucleation is stunted because of poor micromixing.
Your time is up. You should wrap it up and go to conclusions.
Okay, I'll wrap it up in 2 minutes. Okay. So here we see that I've used a cavitating device. So first I used a mixing inside the stream, and this is where the mixing occurred inside the stirred tank. And mixing inside the stream gave us a very good narrow and small particle size distribution, because this time the micromixing is better when it occurs inside a tubular stream. And then adding a cavitating device causes smaller particles to appear. And if we keep this going on for very long times, I'm sure that we'll start seeing a bimodal distribution as well, with smaller particles forming further and further. So then we did a continuous crystallization experiment, which is to just see the effect of the mode of operation on the yield and productivity. And we compared that, and we saw that the yield is fairly unaffected, but the productivity increases for the continuous case by almost 2 orders. And this is usually because of, there are several reasons why continuous process give us better productivity. One of them would be there is no downtime or charge time between the batches. There is no cleaning time. So I just wrap it up quickly now. Thank you. If there are any questions, please type them in the chat.
Thank you very much for your presentation. Surely there will be questions posted for you on the question and answer box. So I will move to the next presentation, which comes to us from the United Kingdom. The title of the presentation is Online Monitoring from Nanoscale into the Micron Area. And the presenter is Stephen Ward-Smith from Malvern Analyticals.
Good morning, everybody. I assume everyone can see the screen okay and hear me?
We can hear you and see you. I do not see the screen.
I have shared. Let me kind of unshare and try again. Yes. It helps if you actually then click the share button after setting it up. Right. Is that okay?
I do see that the sharing has started, but yes, yeah, it is fine. Yeah, thank you very much.
Good, good. Well, welcome everybody. What I'm going to be talking to you about for the next 10 to 15 minutes is some preliminary results from an EU project I've had the pleasure of being involved in for the last 3 and a bit years now, which is called PAT for Nano, which is a Horizon 2020 project. So right. So one of the goals of the project, let me just minimize that. Was to really really look at online particle sizing tools. We've seen a lot of those this morning, but here we're kind of like, I guess there is going to be some crystallization. It's more of a secondary objective. This is more concerned about going down than going up. So we're more concerned really here about micronization and processing more into the nanoscale. And a lot of the time, though, when it comes to end of a mill run, it becomes almost a guessing strategy to work out where you are, or you're having to take samples and measure offline. And there is, yeah, it becomes quite difficult to really get an accurate endpoint. And from an energy perspective, milling costs a vast amount of energy. And if anything we can do to get right first time and reduce the energy burden and hence the environmental burden is going to be a good thing. So we want to create inline and online continuous data, increasing process control, and really get a better idea of refinement of the process. So you can improve product quality, reduce costs, and be more resource and energy efficient. And the project itself, we've got a couple of technologies which we'll mainly be talking about today, which was kind of like the ones that were really ready for prime time and actually putting into plant trials. But we had a lot of other partners who were able to use a lot of more kind of grab samples and processes to refine their early technologies, and they may be more the technologies of the future. So in terms of nanoparticles, because we've talked a lot about micron-sized particles here, they, again, like their big brothers, the shape, the size, and the distribution play a very important role of really what they do. But real-time monitoring is something that has been a little bit neglected compared to a lot of the micron size adoption as such. So here really we are, as I said before, we're really looking at the bottom end rather than the top. So what the objective of the project really was to look at particle size analysis. I'm here principally to talk about laser diffraction, but I've got some DLS results here anyway. We've been working with TNO in the Netherlands. We've got we've both got exactly the same setup, an adaptation of a mastersizer with some special extra bits and pieces to make it at line and put onto a bead mill. So we've developed a sample loop with TNO. So we're looking at dilution of the concentrated nanosuspensions to really look at the process and help monitor endpoints. And we started in the lab. What we're currently doing at the moment, I mean, the project has suffered from COVID delays. We are now, we got a 6-month extension from the EU, but we're now in really the business end of the project. We currently have 2 plant trials ongoing and a 3rd about to start. And the DLS technology is also involved in multiple plant trials at the moment. So we're looking at real-time monitoring of particle size while speed milling. So we're going from large-ish, probably sort of like 60, 70, 80 microns starting material, right down to 60, 70, 80 nanometers, medium-sized finishing material. And the main partners here are involved in the pharmaceutical industry, looking at nano-sized medicine. The smaller you go, the better the dissolution is. Printing industry, pigments, large particles block inkjet heads and are anathema. So really processing and absolute removal of large particles is what that industry is about. And obviously for catalysts, smaller particles, better surface area, better reactions. The technologies we've used in the project have been laser diffraction, which is really my thing. But we've also used dynamic light scattering. A Dutch company called In-Process LSP have been the main partner here. TNO have got an ultrasound solution. University of Galway have contributed to Raman spectroscopy, but so have In-Process. And we've had UCL doing electron microscopy. And we've also had the Fraunhofer Institute doing a different solution for dynamic light scattering. But so what I'm mainly going to be showing you today is some preliminary results for some of the pharma and some catalyst support for alumina and the laser diffraction, but I've got some DLS as well. So we've this is the TNO setup, which was a Centrex silicon carbide inline milling chamber with yttrium zirconia beads, chambers filled with beads, and it was 80% filled chamber with 10% solids. You've got to stabilize the alumina at a certain pH, otherwise it aggregates. It does need some stabilizer, which means we've also got to take that into account when we dilute with the masticizer and make sure we maintain the pH in our diluent, otherwise you get agglomeration occurring and obviously a false particle size. So we looked at developing the sample loop. Obviously, when you start, you try and work out where's the best place to put the process. It turned out in the end, it was really looking at the entrance to the storage vessel is where we've actually kind of gone for. But there was other places as well, but they were not really ideal for sampling. So so point C is where we actually took the sample from the actual process. Here's some preliminary results. This was a pharmaceutical active. It is active enough that we've sort of had to persuade our health and safety people in the office that it's okay to handle it in our office, but we've got to introduce the samples as slurry and have it shipped to us as a slurry rather than produce it off-site, because we don't really have the setup for really active actives as such. And here you can see we can track the decrease of the particle size. We've got good reproducibility, repeated each sample multiple times. You repeated the Milburn multiple times and they're getting similar answers. And that you see the same with alumina. With that, because there's a lot of surfactants in the stabilizer we mentioned before, you do have a challenge with preventing bubble formation. But we have managed to get around that, but that was involved some quite careful sampling, because we did get some erroneous results. But we have actually put some online imaging kind of in the loop as such, not really for giving the same information that Sebastian was doing, but really as just to check that if we get any that bubbles aren't occurring, or if you have any large particles, that they're real and not bubbles. Nanoparticles tend to be thermodynamically unstable by nature, so their stability is sensitive to environmental factors such as temperature, pressure, shaking, stir, and pH. So we do need to look at dilution. And if you are measuring nanoparticles, you do need to be very careful about what you're actually diluting them in. So it is a challenge for sort of like at-line analysis, is that we do need to carefully look at the dilution medium. You can't always dilute in water because we may destabilize the material. And to follow the process, you need to have a stable sample. We have done some comparisons with TNO, and the results were very, very good. This was basically one of us. We've done it both ways. We've milled samples sent to TNO, TNL milled samples sent to us, because even, our mill setups aren't exactly the same mill. So it's hard to run two mill trials right next to each other and get exactly the same results. But we've shared samples and got identical results on the setup. So we're fairly confident we've got a robust sort of sampling and dilution mechanism occurring. And I promised some DLS results. Here we see the pharmaceutical active in the bead mill, and we're able to follow the Z average and the polydispersity index, which are the kind of bedrock parameters for dynamic light scattering measurements. And again, you can see the results track. What we kind of envisage is this is more like a relay race. The DLS obviously can't measure the large particles. So because the top end of DLS is really, you can stretch it to around 10 microns, but just a bit under. But we're starting at about 80. So you'd be looking at starting with laser diffraction and then handing over to DLS, and that's some of the plant trials we've done. We've been working in parallel, and that's some of the results we will present in the future. Is really looking at kind of multi-pack techniques between sort of DLS and laser diffraction. So the current work we're doing, because this is really the all hands to the pump business end of the project, because we finish in October, is really plant trials at all the partners, generally using the in-process DLS and the outline master slicer setup. And we have done some bottom up as well. We've got some initial results, but they've only come out in the last couple of weeks, and I couldn't get clearance together to present today. I tried, was really looking at initial results on Sopat synthesis, really from the nano to the micron, and that looks very promising as well. So we can track the process in milling going down and crystallization or other effects kind of going up. So the current activities, here we said, multiple plant trials. We've got 3 going at present, 1 about to start. The one at AGFA for DLS started last week. There's a blog at patfornano.com which covers that. We've got one at Johnson Matthey, and another one at Janssen, and another Janssen at a different plant about to start. So we're in the process of gathering lots of data before the project ends in October. For those of you who are interested, I think it will be online as well. There's nanotechnology crossing borders, which will be available for registration very soon, will function as our closing meeting, and we're going to have pretty much a day presenting Patfornano results. One of my other hats is I lead the dissemination end of the project, so I will be working hard to make sure that event is a success. And for those of you on the continent, it's at Hasselt University campus Diepenbeek in Belgium on the 24th of October. And these are the partners for the project, which I'd like to thank as well for that for the last few years. So AGFA, TNO, Janssen, University of Limerick, which that is now UCL because the academic moved, University of Galway, Fraunhofer Institute, Johnson Matthey, in-process LSP, Janssen and AGFA. Okay, right, and I think that is me done. Thank you very much.
Thank you very much, Stephen, for the very interesting presentation, and also for keeping the time. So we are now at the last presentation of the session, which comes to us from Denmark, from Novo Nordisk. And the speaker is Isabella Juhl Jorgensen. I hope I pronounce your name correctly. While you start sharing your screen, I'm gonna read the title of the presentation, which is Monitoring an Amorphous-phase Mediated Crystallization Using Process Analytical Technologies.
Yes, thank you very much. And do you see the presentation now?
Yes, we do.
Yeah, well, thank you for the introduction and for having me present here. This is part of my PhD project, which is a industrial PhD project between Novo Nordisk, who's a pharmaceutical company, and Technical University of Denmark. So what this crystallization that I have been looking at is actually for a drug product. So it's not the API crystallization, but for the final product. Because in insulin treatment, or the diabetes treatment with insulin, you have several needs. You would like to have
insulin that is rapid acting, so you can take it before a meal, but you also need to have some sort of a long acting insulin. So this is where the crystals come in. So if you have the insulin in crystal form, then you have a protracted effect. So the product I have been working on, it's actually a biphasic drug product, meaning that an amount of the API or the insulin is then crystals, and the other ratio is then dissolved. So you have both a fast and a slow acting profile. And it's a quite old product. It's been on the market for over 20 years. And I can take you through the manufacturing process. So how it works is that you have the API and excipients, and then you mix it. Then you do an in-process control of the pH. And when you mix them together, a fraction of the API then precipitates into amorphous particles. And it's from these amorphous particles that we then have the crystal formation. So it's not, we don't have a clear solution to begin with, and then crystals coming out of that, we already have the amorphous, and it makes it a little more difficult to monitor it. Then you let it crystallize for a validated time, and then you do some in-process control in the end. You do a microscopy to check whether you actually have the crystals. Then you can fill it into the vials. Then you do quality control, and then you can send it off to the customers. So the question that I kind of been working with is, how can PAT help us monitor this process? And I will show 3 examples. So one is that we can use it to make a soft sensor to predict some of the critical quality attributes. Then generally it helps with process understanding, which can lead to process optimization. And furthermore, also to use it for multivariate statistical process monitoring or control for fault detection. So the technologies that we work with is we have a Blaze matrix probe, and just briefly, if you don't know it, it enables you to have chord length distribution sizing, you get turbidity, and you also get a Raman. Or we have it coupled with a Raman spectrometer, so we get Raman signal as well. So the first part was then to make a calibration, and because what you really check after crystallization is it has the amorphous transformed into crystals. So we needed reference values. So we had a setup with a SAX machine here, so a small angle X-ray scattering, and you can see that we did a small flow through setup with the SAX, and then we had the Blaze probe in the crystallizing solution there. So with the SAX, it's very nice because you will get these Bragg peaks when you start having crystals, and then we can use those as a reference value. So you can see how these Bragg peaks increase during the process. So based on that, I made a PLS regression calibration using both the chord length distribution, turbidity, and Raman data. I did try to see, do I only need one, but I actually got the best results using all 3 types of measurements. And then also I did calibration to predict the dissolved API and also phenol, which is there as an excipient, but actually is also works as a ligand for the proteins, because you have, I won't go too much into that, but yes, they're not just present as an excipient as a preservative. So based on these calibrations, we can then start to look into how the process dynamics are. So we can see how through the process time, how we have the crystallization of the API. We can also see we have a slight change in the dissolved API with time. It's not a huge change, but there is a slight change. And we also saw, and we weren't really aware of this, that the amount of phenol that is in the dissolved phase actually increases. So this is then related to the phenol that is not bound in the crystals. Then we could look at the chord length distribution. So if we have the chord length here, and then we have the normalized process time on the y-axis, we could see that in the beginning we have some very small, or we have a large fraction of very small particles, which then, or small quarks, which then decreases, but then we get a larger fraction of small quarks again for them to disappear. And if we look at the median chord length instead on the right axis, then you can see the same trend displayed here. You have an increase here in the chords and then a decrease. And if we compare that then with the other, if we do an overlay then and look at the other dynamics we have in the process, we can see that this change occurs maybe around when 20% of the API has then crystallized. So the crystals are needle-shaped crystals, so you will have a large portion of the quartz being very small. So this is sort of how we interpret it, this drop then in the chord length. So unfortunately, you can't use it for the onset of the crystallization because then there's still not enough crystals. But it's very interesting to have these different dynamics together and see how they can contribute to the understanding of each other. And then to the process optimization. Well, ideally, we would like to have this inline measurement and then move towards Pharma 4.0 or Industry 4.0. So ideally, we could do the inline in-process control, but also have the flexibility to not use it just to say we have a validated time and then we measure with the probe instead, but have it more free, so that when you hit a certain target, you would be able to release it for filling. And then, of course, we are also moving just in the beginning, going towards inline quality control, but that is a long way or a lot of work that needs to be put in there. But just being able to measure some of these critical quality attributes inline really helps. And this leads me on to the next topic, because very closely related to quality control is then also multivariate statistical process control and fault detection. So in MSPC, then you have some sort of input, right? And you have a process, and you know how that affects your CQAs, which in our case would be drug product efficacy. So that would be dissolved API as a crystalline API because of the different action profiles, and then a crystal size distribution as well. So if you really know a lot about your process, you know if something happens, for example, to your raw material attributes, then you know how it affects your product in the end, and then you could be able to do something beforehand. However, sometimes we don't know everything about a process. So if something changes here in the input, or maybe we're just simply not measuring all the right things, then we don't know how this would affect the drug product efficacy. But this is where then MSPC come in as a tool. It's not the final solution for everything, but at least this enables us to do monitoring throughout the process and see, does the process look as it's supposed to, so we don't discover it in quality control, but are actually able to do something beforehand. So I'm not going to go a lot into the development of the models, but of course you can answer questions. But basically, we did a PCA-based monitoring scheme. So what you monitor is the square prediction error and a homogeneous t-squared. And then you just can create some upper control limits based on your normal operating condition batches, and then you can monitor if these two metrics are going out of control. So in MSPC, what you're really interested in is, of course, you want to have a high fault detection rate, meaning so if a batch is faulty, you really want to know it, but you also want to have a false alarm rate, meaning that you want to ensure that NOC batches are not flagged as faulty at some point. And then a way to kind of weigh these, of course, there can be economic reasons for going with either high, or saying that if the fault detection rate is much more important, or that false alarm rate is too costly. But we did a model just based on where we don't do any weights, but we tune the models with regards to accuracy. So that's giving equal weights to the fault detection rate and false alarm rate. And then for the model, we had 12 NOC and normal quality batches, meaning that they were on specification, and we had 6 where we had abnormal operating conditions, which resulted in off specification. And these were 6 different types of faults. So it was, we had too much water, we had a missing excipient, we had different pH, too low zinc. So different varieties that we wouldn't normally measure. Until quality control. And then we tried 2 different ways. So when you do MSPC with different types of data, so data fusion, there are different schemes. Oh no. Just a second, sorry. Okay, now you see my screen, sorry. So what you can do is then you can do low-level data fusion, where you just take all of the data and have it together in different blocks, of course, with some scaling, but you would have a large weight of the spectral data because you have 2,000 variables there compared to the turbidity, which is 1 measurement. So we also looked into doing mid-level data fusion, where you do some sort of dimensionality reduction first. So that could be a PCA in our case. So you do a PCA in the card length distribution and a PCA in the spectrum, then you use the scores as variables in your monitoring scheme. There is also the option to do a high-level data fusion, where you would then use the soft sensors, for example, that I created earlier, and use those as variables. But we wanted to also see if it would be useful, or is it even necessary to develop those in order to get a good monitoring scheme. So we didn't do that here. And it turned out that we were able to achieve, with the low-level data fusion, an accuracy of 92% and an accuracy of 75% with the mid-level data fusion. And then we have thought a lot about this, and I've gotten questions about it. My feeling would be that you lose too much information with the spectra when you do the PCA first. I've read a study where they did it with NIR instead, and they got better accuracy doing the mid-level data fusion. But that could also be something related to how in Raman spectra, for example, you have very sharp peaks, and maybe you lose more information doing the PCA compared to NIR. But that is something to look more into. So hopefully I've kept the time. I think I have. So the conclusion is that, I have shown that with process analytical technologies combined with chemometrics, we were able to create soft sensors for secure predictions that the process understanding enables, or the process understanding that it comes from the PAT enables process optimization, and that we could also get a nice multivariate statistical process monitoring scheme without using the previous CQAs, but just using the data from the PAT sensors. And so I want to thank you for listening, and also want to thank my supervisors and collaborators at Novo Nordisk, and also our collaborators at University of Padua, where I did a research stay. Yeah.
Thank you very much. That was also very nice and interesting. Thanks again. All right. So we are at the end of the presentations, only a few minutes late. So my suggestion would be that all the speakers switch on their cameras, and we can do different things. Indeed, there are questions that were asked in the question and answer box, and the answer was already provided in written form by the speakers. So maybe there are some of the questions posted there that would be useful to be re-asked and discussed publicly. But before doing that, maybe I'll start with a question that is for all of you to answer. Probably Sebastian and Stephen from their industrial perspective would like to say something about this. So this morning we saw different crystallization techniques, different crystals and amorphous particles produced in different ways, but we also saw different characterization techniques. Some of them were offline characterization techniques, some others were online characterization techniques. So I remember when the first probes entered the market. I was a PhD student, so that goes back to almost 20 years ago. And there was a lot of skepticism about these techniques. Then, of course, these techniques have improved, and also many different new technologies have been introduced. So the question is, what is the future of the standard, all the offline techniques, static light scattering, dynamic light scattering? How can they be used in conjunction with online techniques? And where do you need one, and when do you need the other? There's also, as I said, this is a question for all the speakers, but again, as I said, maybe Sebastian and Stephen want to break the ice.
I mean, I guess lab technology has been around a very long time, but you're not. But the problem a lot with online is you don't always get the same answer as the lab, and then you've either got to look at models or correlations to try and do it. So if possible, it's always best to try and take the same technique and then put it online if you can, or have a lab equivalent, because it allows for easier comparison if it's possible, which isn't always. So which is why we do have another laser diffraction piece of equipment we often use for kind of crystallization, but with this, it's with the one thing I presented, it's a masticizer, so it will give exactly the same answers as a masticizer in the lab, because it's exactly the same optics and setup as the lab. So if you so I think that's one route, is to try and take what's on the lab and take online, or take what's online and develop a lab alternative. For probes, it's easy to place in a beaker, and you can have a lab instrument as well, because then if you can get the similar answers, it means people will have the confidence to do real-time release, which is where I think a lot of the gain is actually going to be, because then you don't need to wait half an hour for QA to get a final sign-off. You know, once you've got that answer, you're then confident that you've reached where you want to be, and you can just let the product out.
Anybody else who wants to add a comment on this?
I think at least what I also hear in the discussions in Nova, because we really want to move towards a real-time release, is also the worry that the inline measurements are not as good as the lab. And how do you take that into account? But also you have to take into account the sampling errors that can happen when you go from taking something in your process and going to the lab. So also considering that, I think is very important and should be emphasized as a gain for the inline measurements.
Isabella raises a good point, because one of the main reasons what gives people confidence is validation using standards. And the problem is, which is how do you validate using a standard on an online technique in a similar way without necessarily contaminating your process? So you've got to take something kind of offline to put a standard in, and then put it on kind of online as well. So validation can be a little tricky.
So may I add something to this?
Sure.
So I think this is a very interesting question, and it's in a way ultimately related to scaling up. And once we think about taking a lab scale probe and installing it, we have to, of course, make sure that at least, as mentioned, for the standards, you should get the same results. But it is also interesting to see that in a process, the hydrodynamics would be different. Therefore, the dynamic aspects should be different, and we should not be surprised about that.
And maybe to continue, so I would say quality assurance labs will exist, especially in the food and pharma industry, just because on regulatory demands through the next century. And this is good because we do want to know what we need or what we get in a hospital. We do want to know what we eat. So this is, I think, in terms of laboratory equipment, will be necessary for the next 100 years. Parallel, if we're not only talking about quality assurance, but also about process optimization, and in the 21st century being significantly confronted with the need to make things more efficient, I think this is where we do need to discuss online solutions. And especially if I think about organic crystallization applications, where you have a lot of natural products coming into the process, where you have high variations in the feed and things like that. And the larger the scale of the production, the more likely you do have changes and instabilities. So I think this is clearly the direction where I do see increasing demand in online monitoring technologies. So I would say we do need a both-and approach, because quality assurance is important, quality assurance is necessary. Trained staff in a QA lab is important for our own health. But in terms of an engineering perspective, process optimizations are very, very important and very, very necessary. And the more challenging and the more complex the crystallization, the more you can do with online tools.
Another point that clearly emerged from the presentations is the incredible advancement in terms of morphology and shape, which again, it's something that 20 years ago was very difficult to do. So now we have all these tools that can characterize particles and crystals in terms of their three-dimensional features. And I guess the question is, how do we use them to control a process? If we have a simple, feedback control strategy, temperature, concentration, then things usually are easy. But then when you have many processes, many phenomena, nucleation, growth, aggregation, and breakage, non-linear relationships between the different factors, then I guess one question is, yes, now we do have all these tools to characterize the particles, not only in terms of size, but also in terms of shape. And then what do we do with it? Again, especially online, to control a process. And I guess a very last part of the question is what was asked by Alessio Lavino on the Q&A box, related to the role of artificial intelligence, neural network, which have been developed to process many different pieces of information, including images. So I guess the last part of the question is, could neural networks, machine learning, artificial intelligence in general, be the missing element to link monitoring shape and size with process control? What do the speakers think about this?
Absolutely. That is the missing link. And this is already, I mean, the one challenge which we are close of overcoming is the input data for the neural networks. I mean, what we do find out is the quality of the training describes then the quality of the results you get out of a neural network. However, if you are able to create training data automatically without human interaction, then you can create perfect training in no time for almost every application. And if you have solved that, then the applications are endless.
And I think the other side of that is our responsibility if it, as instrument manufacturers, in terms of the output, is to basically try and up our game when it comes to file formats and stuff, to make sure we've got maximum flexibility, so anyone can put rather than cut and paste or whatever, to easily get their data into training algorithms as well.
Anyone else wants to add anything on this?
Well, maybe regarding the shape or the automatic generation of shape of crystal training data, which I think where crystal shape modeling really can help a lot. And I think we saw also in Ashwin's talk that they used that very successfully, that they were able to generate differently shaped particles and then train their method on that. And that is something where you, I guess, can benefit a lot for these calibrations, basically, and then generate data where you basically know the ground truth, and then hope that your real process behaves similarly.
If I may, just to add to Simone's point and also to what was raised before, right? I think for me, even before going to the aspect of controlling a process, I think modeling a process is more important, because I think over the years we have done 1D modeling, we have done 2D modeling, but we've never done it in a scale that we should be doing, so that we are comfortable with really understanding the systems that we have. And once we know what is actually happening, building a process control strategy is not that complicated, because you know what is happening, you know what you'd expect. So designing a controller is not going to be a blind game anymore, right? So to me, I think the first place where I think this powerful size and shape characterization tools will come into play would actually be in the modeling and actually helping us understand what is happening in the process. This is something similar to what happened when the IR became more accessible to people, right? So we started seeing more and more models that started using the information that comes from concentration measurements real time, and that in turn helped us, come up with better strategies to operate the process as well. So before control, I would probably do the modeling part. So that's my take on this.
Yeah, thanks for the comment. Which is also bringing up another important point related to modeling. So, of course, we have these neural networks and machine learning tools that are extremely powerful. They can digest very large amount of data related to size distributions and shape and other properties. But then, of course, they do not give you an insight into the process. The insight comes from the model, but the model needs to be fitted, because we are dealing with stochastic processes, which are very difficult to fully characterize. So at the end, there are some uncertainties which come up into the model in the form of unknown model parameters, which need to be fitted. And of course, one criticism, and I usually do this, I develop models and then I feed them. But then one criticism is that you change one tiny thing in the process, you change an additive, you change even the surface property, maybe of the impeller or something else, and then the kinetics of your semi-empirical model change. So of course, one solution could be to take data from experiments, data from simulations, and then use machine learning to do the training. But I'm also interested in hearing what other the speakers have to say. I remember conversations on this point of modeling a crystallization process and how difficult it is with Elena. I don't want to put you on the spot. I also see that Eral has raised his hand, as well as Simone. So I mean, everybody's free to speak.
Yeah. So regarding the model, so I think people that are involved with modeling, they all know that fundamentally all models are wrong. So the question is how wrong it is. And we always need to make, let's say, the physics is happening in this beautiful system, and then we always have to, we can't incorporate all of the physics, and we make choices. And I think the more accurate our choices become, the more reflective of the reality, then I think these problems with the problems of changing something and then, you know, seeing a very huge effect on the result will decrease. And one thing, one recent progress that I can tell you about is particularly in physics-based predictions. Yeah, so in the sense that when you start with a machine learning algorithm, right? So it is always a mathematical concept, and the more of the physics that you can incorporate in, it helps you to screen the data in a more accurate way. And I think ultimately this is not only a challenge that we have to deal with. I think it's just all engineers have to deal with this kind of uncertainty, and I think if we talk to each other, we have a better chance of handling this challenge.
Simone, I think you are next by looking at the ends.
Yeah, so basically pretty similar to what Burak said, that I think that the mechanistic modeling thing is something that really can help you. Like you mentioned before, the example where you said maybe if I change this impeller speed or something, that changes my process. And that's of course something we could in principle include in our modeling. And then of course that becomes very sophisticated in the end, such models, but which might be too sophisticated for like inline monitoring or stuff like that, but can really help us to understand what is happening. And once we understood what is happening, we can think about control and maybe build a model that kind of accounts for stuff like that, and then use that for training of an artificial neural network, which will then be fast enough for control. And that is, I think, something that could be a good approach. Of course, not an easy one, but maybe a good one.
Ashwin?
Yeah, so just to add to the points that were previously made, right? So I really like this quote, which is a model is only as good as the data that you feed inside, right? So if you don't have good data, the data that, let's say, if your measurement of the process itself is not good enough, then the data that you get is not reflective of what is happening inside the process, which is why in many cases, like the example that you gave, your models might fail because you have not incorporated in your model the effect of, let's say, surface properties, or let's say crystals break. You assume the particle, like what Simone showed, you have abraded particles, but you usually assume that, yeah, the particles are perfect, you know, they are nicely faceted, but probably they are not, right? And I think that's where the challenge is. If we actually don't know what is happening from a wide range of properties that we are usually interested in, it's hard to build models that are scalable, that are also predictive across different, let's say, even doing at different labs. So that's sort of my point. So I think that's where investing more on these resources to really track the fundamentals or what is happening inside might actually help us build better predictive and transferable models. And then, of course, adding to that, you can have machine learning models to basically speed up everything, and you can use it as a surrogate to do control and things like that. So that will probably be my take on this.
Elena.
Yeah, I think this kind of like takes things from people that people have already said, but as an experimentalist, so I struggle a lot, for example, to just get size distribution of particles. So I haven't found a technique that gives me the right size distribution. And I usually have to use more than one technique, combine lab techniques with online. So just going back to one of the first questions that you asked, do we still need lab technique? Yes, I think we do. And then again, you look at the images and you're like, okay, but still, how do I translate this with an actual, parameter that I can fit in the model? So we have to make assumption as also Carol was saying, and the model is not perfect. My approach, I guess, has always been like, try and put as much information as you can get from different tools, and perhaps that's another way of using machine learning, so to deal with large amount of data from different tools. And again, I'm not a modeler, so sometimes I go on different ways with the model-free control approaches, where you rely more on the signals from the tool, and you kind of just say, okay, maybe I don't know much about the model, but I can still control the process. So I think that two things has to go in parallel, and we have to accept some limitation on one and the other. I don't know, maybe it's a bit too cynical, but.
Yeah, no, I tend to agree to what you said. Thanks, Elena, for sharing your thoughts. I see that Stephen has raised his hand. I just want to mention that we should probably wrap it up in 5 minutes because at a certain point the virtual session will expire, and it would be weird to have it shut it down without the time to say goodbye to each other. Please.
Following on really from the last two panelists, which I completely agree with, I guess the challenge for anything optically is a lot of its concentration, because you've got things like multiple scattering kind of occurring, which generally tends to create false finds, which means kind of particles aren't there, or then things which will be happening in the process, which won't necessarily be in the lab when you dilute, and things like particle-particle interactions, which will kind of occur as well, which can change the answer. And these are all things that you need to kind of get your handle on when it comes to, as was just said by Ashwin, that to get better data to better inform the models. Almost certainly, yes, it is the future, but we need to, we do need to, I completely agree, to try and get the best data as possible. Otherwise, we're just going to get nonsense.
Thanks. Vidit, please. You are muted. We cannot hear you.
Can you hear me?
Yes, now we do.
Yeah. So I heard all the panelists talking about different characterization techniques, and one of the challenges that come across is different techniques will give you different kinds of particle sizes. Some will give you length-based particle sizes, or length-weighted, volume-weighted, area-weighted. So I think it is important to understand which kind of particle size is essential to your application. For example, dissolution studies would require area-weighted particle sizes, because more surface area surface area affects the dissolution rate. Or even growth, if you're trying to model growth, there you would like to have like area incorporated into your particle size distribution. So I think that should be kept in mind while choosing the different, like which particle characterization technique you're using.
Yeah, that's also a very important comment. I think we need to wrap it up. So Martin and Martin, I'm not sure if there is something you want to say. I just want to thank all the speakers for their excellent presentations, and also all the participants for attending and for asking challenging and nice questions. I'm sure I'll see many of you at the several events sponsored by the European Federation of Chemical Engineering. Again, B-Week in Stockholm at the end of August, the ISIC or ISIC in the beginning of September in Glasgow, and the European Chemical Engineering Conference in Berlin at the end of September. Anything else from your side?
No, thank you, everybody, and see you in the next webinar. Bye.
Yeah. Bye-bye. Thank you very much.
Bye-bye.